Modern robotics pursues a single objective, a vision language action model, or VLA, that can generalize across unstructured physical environments without task-specific programming. The models currently approaching this threshold share a common set of failure points. They are either closed, proprietary systems locked to highly specialized hardware, or they operate with too much computational latency to handle closed-loop physical control. This latency is heavily compounded by explicit reasoning. When a policy pauses to generate hundreds of tokens for a chain of thought trace or a complete scene depth map before taking an action, the control frequency collapses. The robot cannot react to the physical world in real time. Molmo Act 2 is designed specifically to resolve this gap between semantic reasoning and kinematic execution. It is an open-weight, hardware-agnostic VLA, engineered to maintain high control frequencies during real-world deployment. The architecture is the result of a collaboration across several major research institutions, including the Allen Institute for AI, the University of Washington, and the National University of Singapore. Their system relies on three structural components: a visual backbone specialized for spatial geometry, an architecture that bridges discrete token prediction with continuous motor control, and an adaptive depth reasoning algorithm that bypasses traditional latency bottlenecks. Reaching state-of-the-art performance requires moving past simple model scaling to re-architect how a system perceives space and handles temporal change. General-purpose vision language models lack the physical intuition required to operate a robot arm. They struggle with metric distances, with spatial occlusion, and mapping an egocentric camera view to a third-person exocentric perspective. To correct this, the team built Molmo 2 ER, an embodied reasoning backbone. They trained it on a 3.3 million sample corpus using a specialize then rehearse recipe. Standard web data is filtered out and replaced by datasets focused on image pointing, video embodied Q&A, and ego-exo correspondence. Training on these specific pillars forces the model to develop highly localized physical awareness, resulting in pixel-accurate pointing and the ability to track objects seamlessly across multiple camera views. With the spatial backbone established, the model needs to learn movement. However, training a standard text-based VLM directly on continuous robot motor outputs is notoriously unstable. To stabilize the training pipeline, they utilize the OpenFast tokenizer. This tool compresses 1 full second of 32-dimensional continuous robot trajectories into a compact sequence of discrete, text-like tokens. This allows the system to map both language instructions and physical actions into a unified next token prediction framework, identical to how a standard language model learns to predict the next word. While discrete tokens guarantee a stable multimodal pre-training phase, real-world robotic motors operate on dynamic, high-frequency, continuous signals. The system must translate discrete reasoning back into continuous motion. The architectural solution involves taking the pre-trained, discrete VLM backbone and attaching a continuous, flow-matching action expert, specifically a diffusion transformer. Previous attempts at this interface typically pass only the VLM's final layer hidden states to the action expert. This strips away the rich, hierarchical visual and semantic features that the network builds up in its earlier, shallower layers. Molmo Act 2 bypasses this data loss by introducing the per-layer key-value connection. Instead of a single handoff at the end, the VLM and the action expert are matched layer for layer. At every block of the architecture, the VLM's key and value tensors are extracted and fed directly into the cross-attention modules of the action expert. These incoming hierarchical tensors condition the action expert. It uses this dense data to guide its velocity field generation, systematically denoising a randomized action trajectory into a smooth, continuous path. Because the connection exists at every depth, the continuous controller has direct access to the exact spatial and semantic features the VLM is processing at every level of abstraction. This dense connectivity bridge ensures that the final continuous kinematic output is guided by the model's full spectrum of discrete semantic reasoning. Giving a model explicit geometric grounding, requiring it to predict depth maps before it takes an action, measurably improves its success rate in complex physical environments. The standard implementation requires the model to auto-regressively predict a 100-token depth grid at every time step. Generating that many tokens repeatedly causes the control frequency to drop below the threshold required for fluid movement. To retain the geometric data without the latency penalty, the team developed a variant called MoMo Act 2 Think. It works by exploiting the temporal redundancy inherent in physical space. This diagram illustrates the concept. Focus on the top row, showing the camera perspective from t equals 0 to t equals 1. In any standard robot trajectory, the vast majority of the background scene remains static between frames. Rather than regenerating the entire depth grid, the model isolates the specific spatial patches where the visual RGB evidence has changed, shown here as the localized blocks tracking the moving arm, and triggers the adaptive update pathway for only those regions. The system reuses the cache depth codes for all static regions. This significantly reduces the number of tokens the model must generate per frame, formatting them into the adaptive depth perception tokens, feeding directly into the action expert. The computational cost of geometric reasoning now scales only with the dynamic changes in the scene. The model maintains its strict 3D grounding at a fraction of the prior latency. Simulation benchmarks prove a model works in a sterile environment. The defining test for a VLA is out-of-distribution, real-world deployment on affordable hardware. This chart details performance across 8 distinct in-the-wild bimanual tasks, using the low-cost YAM ARM setups shown below. Looking closely at the final cluster, MoMo Act 2 in pink outperforms proprietary models like Pi 0.5 and open alternatives across almost every task category. The quantitative result is an average success rate of 50.1%, establishing a 15% performance gap over the closest competing architecture. Task success requires accurate logic, but smooth physical execution requires a high control rate. To maximize this rate, the engineering team cached intermediate cross-attention states and captured the fixed-shape flow loop with CUDA graphs. This optimization bypasses the software overhead of launching repetitive kernels. The resulting control rate jumps from a baseline of 23 Hz to 55 Hz, providing the high-frequency refresh rate necessary for fluid, closed-loop reactions to sudden physical changes. Alongside the model weights, the team released the underlying infrastructure, 720 hours of teleoperated bimanual YAM trajectory data, highly filtered internet datasets optimized for the $150 SO100 ARMS, and the complete open-fast tokenizer codebase. This open-weight release provides researchers and smaller institutions with the tooling required to run state-of-the-art physics models without relying on proprietary hardware or closed corporate data moats. MoMo Act 2 establishes a fully open operating architecture for the physical world, proving that frontier-level robotic intelligence can be engineered for universal access.